Oracle access paths refer to the different methods by which Oracle database retrieves data from a table or an index. The database engine uses various access paths to read and retrieve data from tables based on the SQL statements issued by users. Here are some of the most commonly used Oracle access paths. 1. Full table scan. This method reads all the data from a table and is useful when accessing a large portion of the data. 2. Index scan. This method reads data from an index rather than from the table itself. It is used when a small amount of data needs to be retrieved or when a specific subset of data needs to be accessed. 3. Bitmap index scan. This method uses bitmap indexes to quickly retrieve data from a table. For hash join, this method joins two tables using a hash function to match the rows between them. 5. Nested loops join. This method involves using an index on one table and then joining the rows from the other table. 6. Sort merge join. This method sorts the data from two tables and then merges them to perform a join operation. 7. Clustered index scan. This method reads data from a clustered index, which is an index that has the same physical order as the underlying table. The Oracle Query Optimizer determines the most efficient access path based on the available data, statistics, and other factors. As a developer or DBA, it is important to understand these different access paths and how they can affect performance when designing and tuning database queries. In Oracle, a full table scan is a type of table access method where the database reads every row in a table to satisfy a query or operation. This means that the database reads the entire table, even if only a small subset of the rows is required for the query result. Full table scans can be efficient when querying small tables or when the query requires all the rows in a table. However, when querying large tables or when only a small subset of the rows are required, full table scans can be inefficient and cause performance issues. To improve performance, Oracle has several mechanisms for reducing the need for full table scans, including indexes. Indexes allow for faster access to specific rows in a table, reducing the need for full table scans. Partitioning. Partitioning a table allows for the data to be split into smaller, more manageable parts, which can reduce the need for full table scans. Materialized views. Materialized views are pre-computed queries that store the results in a table, reducing the need for full table scans when running the same query multiple times. Query optimization. The Oracle Optimizer uses various algorithms to determine the most efficient way to access data, which can reduce the need for full table scans. Overall, full table scans can be useful in some situations but can also lead to performance issues in others. As with all database optimization, the best approach is to understand the specific requirements of the query or operation and use the appropriate techniques to minimize the need for full table scans. An index scan is a technique used by the Oracle database to efficiently search and retrieve data from a table based on the values of one or more indexed columns. In an index scan, Oracle uses the B-tree index structure to traverse the index and locate the relevant rows in the table. The B-tree structure allows for efficient searching of the index based on the indexed column values, as it enables the database to locate the specific data block or blocks that contain the indexed data. Index scans can be very efficient for retrieving data from large tables, as they allow Oracle to quickly locate the relevant data without having to scan the entire table. However, they can be less efficient if the index is not well designed or if the query involves non-indexed columns, as Oracle may need to perform additional lookups or scans to retrieve the required data. There are different types of index scans in Oracle. Index range scan. This type of scan is used when the query involves a range of values for the indexed columns. Oracle scans the index and retrieves all the rows that fall within the range of values specified in the query. When a query is executed with a condition on a column that is indexed, the Oracle database engine can use the index to perform an index range scan. This means that the engine can use the index to locate the first and last row that satisfies the condition, and then retrieve all the rows in between directly from the index, without having to access the table itself. Index full scan. An Oracle index full scan is a type of index scan operation that retrieves all the data from a non-unique index in Oracle database. Oracle reads all the index blocks in the index segment containing the data and returns all the index entries in sorted order. In a full scan, Oracle does not use any criteria to select only a subset of the index entries, so it is a more time-consuming operation compared to other index scan methods like range scans or index lookups. However, a full scan can be useful in certain scenarios, such as when a table is small, or when the query needs to retrieve all the data from the index. One thing to note is that a full scan may not always be the best option for performance, especially for large tables, because it may require reading a significant amount of data from the disk, which can be slower than other methods. In general, it's important to analyze the performance of different index scan methods and choose the one that is best suited for the particular query and data set. Index unique scan. It is a type of index access path that is used when the index being scanned is unique, meaning that each index key value maps to only one row in the table. The Oracle Index Unique Scan is an efficient way to access data in a table when the index is unique, as it can significantly reduce the amount of I/O operations required to retrieve the necessary data. However, it is only effective when the search criteria are based on the indexed columns and when the index has a high selectivity, meaning that it can quickly identify a small subset of the total rows in the table. Index Fast Full Scan. An Oracle Index Fast Full Scan is a type of index scan operation that can be used by the Oracle Database Optimizer to retrieve data from an index. It is an alternative to the traditional index range scan or full table scan, but with this data is accessed in parallel and data retrieved is not sorted. The Index Fast Full Scan can be particularly effective when the index being scanned contains all of the columns required by the query. This is because the optimizer can retrieve all of the required data from the index blocks themselves, without the need to access the underlying table. It is important to note that an Index Fast Full Scan can be more resource-intensive than other index scan operations, as it requires the optimizer to read every block of the index. As a result, it may not be the best option in all cases and should be used judiciously. Index Skip Scan. In Oracle, an index skip scan is a technique used to improve the performance of a query when a composite index is available, but the leading column of the index is not used in the query's filter conditions. To enable the skip scan in a query, you can use the skip_scan hint or set the optimizer parameter optimizer_use_skips to true. Oracle hash joins is a type of join operation used in Oracle database systems to combine data from two or more tables. In a hash join, the Oracle database system partitions the data into smaller chunks based on a hash function and then performs the join operation on those smaller partitions. Here are the basic steps in a hash join operation. Partitioning. The database system reads data from the join tables and partitions the data based on a hash function that uses the join columns. The partitioning process divides the data into smaller chunks or buckets, and each bucket is assigned to a hash table in memory. Probing. The database system reads the data from the smaller table, known as the build table, and probes the hash tables in memory to find matching rows. The probing process compares the hash values of the join columns in the build table with the hash values in the hash tables to identify matching rows. Joining. When a matching row is found, the database system combines the matching rows from both tables into a single result set. The result set is then sent to the user or application that requested the join operation. Hash joins can be faster than other types of joins, such as nested loop joins or sort merge joins, because the partitioning process reduces the amount of data that needs to be compared. However, hash joins can also require a significant amount of memory to hold the hash tables, especially for large tables. In Oracle databases, the optimizer decides which type of join to use based on the size of the tables, the available memory, and other factors. It is also possible for database administrators to specify the join type using hints or other tuning techniques. Oracle Nested Loop Join is a type of join operation used in relational databases to combine data from two or more tables based on a specified condition. It is called nested loop because it involves nested loops, one for each table being joined. In a nested loop join, one table is designated as the outer table, and the other table is designated as the inner table. The join process begins by selecting a row from the outer table and matching it with a row from the inner table based on the join condition. If a match is found, the resulting row is returned, and the process continues until all possible matches have been found. The performance of a nested loop join can vary depending on several factors, including the size of the tables being joined, the selectivity of the join condition, and the available hardware resources. In general, a nested loop join is most efficient when the outer table is small and the inner table is indexed on the join column. Oracle Database uses several variations of nested loop joins, including simple nested loop join. This is the most basic form of nested loop join, where each row from the outer table is matched with every row from the inner table. Index nested loop join. This variation uses an index on the join column of the inner table to speed up the matching process. Partition-wise nested loop join. This variation is used when both tables being joined are partitioned. It applies the nested loop join algorithm to each partition pair, instead of joining the entire tables at once. Overall, nested loop joins are a powerful tool for combining data from multiple tables in Oracle Database, and their performance can be optimized by selecting appropriate join strategies based on the characteristics of the data being joined. Oracle Sort Merge Join is a type of join algorithm used by the Oracle Database Management System to combine data from two or more tables. It is an efficient method for joining large tables and is commonly used when other join methods like nested loop join and hash join are not feasible due to the size of the tables being joined. The Sort Merge Join algorithm involves two main steps. Sorting. The data from the joining tables is sorted based on the join key, which is the column used to match the rows from the tables. Merging. The sorted data is merged into a new table that contains the matched rows from both tables. The steps of Oracle Sort Merge Join can be summarized as follows. The data from both tables is sorted based on the join key using an efficient sorting algorithm like quicksort or mergesort. The sorted data is then merged into a new table, which contains the matched rows from both tables. The merge process involves comparing the values of the join key in each sorted table and combining the matching rows into the new table. Finally, the new table is returned as the result of the join operation. One advantage of Oracle Sort Merge Join over other join methods is that it can handle large tables efficiently. However, it requires extra disk space to store the sorted data and can be slower than other join methods for small tables. Oracle Bitmap Index Scan is a type of index access method to efficiently handle queries that involve multiple columns or conditions. The bitmap is a binary string of zeros and ones, with each bit representing the presence or absence of the value for a particular row. A bitmap index scan uses this bitmap to quickly locate the rows that match a particular set of conditions. The index scan reads the bitmap and identifies the rows that match the query conditions. It then retrieves the corresponding rows from the table, which can significantly reduce the number of disk I/O operations required to execute the query. Bitmap index scans are particularly useful for queries that involve multiple conditions or columns, as they can efficiently handle queries that involve complex combinations of conditions. They are also useful for queries that involve low selectivity columns, which are columns with a small number of distinct values. However, bitmap index scans can be less efficient for queries that involve high selectivity columns, which are columns with a large number of distinct values. In these cases, a B-tree index may be more efficient. Additionally, bitmap indexes require more storage space than B-tree indexes, as they must store a bitmap for each distinct value in the index. A clustered index scan in Oracle refers to a method of retrieving data from a table that is organized based on the clustered index. A clustered index is a type of index in which the physical order of the data in the table is determined by the values of one or more columns in the index. During a clustered index scan, Oracle reads data directly from the clustered index structure, rather than from the table itself. This allows for fast and efficient retrieval of data, particularly when searching for a range of values in a specific column. One of the advantages of a clustered index scan is that it can reduce the amount of disk I/O needed to retrieve data from the table. This is because the data is already sorted in the clustered index structure, so Oracle can quickly locate and read the desired data without having to scan the entire table. However, a clustered index scan can be less efficient when retrieving a large amount of data or when searching for data based on multiple columns. In such cases, a different type of index, such as a non-clustered index or a bitmap index, may be more appropriate.